Good morning, everybody. Welcome. Thank you all for joining on time. Today we have Tali Zohar over here with us. And she will introduce herself and we will hear her lecture on, sorry, I want the official name, the dual use of land in agri-photovoltaics. Take it away, Tali. Tali, we can't hear you.
Sorry,
Okay.
I will start from the beginning. Thank you, Abigail. Good morning or good noon, everyone. I'm very pleased to be here, and I hope you will find the next 2 hours interesting. I will introduce myself shortly. So my name is Tali Zohar. I'm mainly dealing with energy policy. My PhD deals with the low carbon transition Israel is supposed to or need to go through for us to reduce greenhouse gas emission and to become more prepared to climate change implication. Is everyone here? Should I start? Yes? Okay.
Yes, you should start.
Okay, so I'm going to share my screen in a minute. Oh my God, sorry. Okay. Okay, so everyone sees my screen?
Yeah, we see it.
Okay. So currently I'm a researcher at the Dead Sea Narva Science Center. It is located at the Lod Regional Council, which is in the southern part of Israel. I'm also joining the Arava Institute, which is very exciting for me. I will present though the research that I'm doing in the Dead Sea Narva Science Center. It deals with the water, energy, and food nexus. And at the beginning, we will start talking a little bit about the global projections towards 2050. Because when we are talking about energy policy or determine any kind of policy, of course, we're looking at the future. And we need to adapt ourselves to the current projections that not only in our states or our countries, also global projections, because in this global world, everyone is affecting everything. So the population of Earth is going to grow rapidly. So we will need 60% more food to feed the entire world population. We will need to increase our global agriculture production. It will require more fresh water, which is already now we're using around of 70% of the fresh water in the world is consumed by agriculture. So the increase will only burden more on the globe. Global energy consumption is projected to grow by 50% by 2035, which is really soon. When we are talking about 2030, it's like talking about yesterday. When we are thinking ahead, we always need to think a few decades ahead. And of course, when we're talking about future projections, we have to talk about climate change impact, because we see it already happening today. We see the droughts, we see the floods, we see the immigration that the population needs to go through because they're suffering from the extreme heat and the extreme the need for water that is not in hand. We see the intense in tropical cyclone activity. We see the major population that is undernourished and suffers from very bad diets. And this is what we see currently now. So obviously it will go and get worse unless we will try to do our best to mitigate climate change and to seriously decrease the greenhouse gas emissions, and of course to limit global warming. This is another very important map that we can see how water stress by country is going to be like in 2040. And you can see that most of the globe is turning red. So that means that it's a very, very high, extremely stressed water that is, it's not, we will not be capable to drink fresh water and to use water. So also you can see on the right map how desertification is really climbing ahead. Also, when it starts at the beginning, most of Africa used to be desert. Also, Europe is becoming very much alike, both with temperatures and both with water stress, and it's impacting all ecosystems and of course human beings. And when we see that, we also see that unlike this Rubik cube, that each side has its own subject. I mean, only land for energy, or only land for food, or only land and resources for water. It's not going to be like this anymore because we are short in resources. So everything is going to be much more stressed, and we will need to use the same land to produce energy, to grow food, to save water. And this is a global effort and a global issue that all countries in the world are facing. I have a little video here.
Tali, we can't see the video.
Okay, so I need to share screen again.
You're sharing the screen at the moment with the presentation, but you need to share the video.
So I'll stop sharing. Okay. Everyone sees the screen now?
Yes.
Now? Okay.
Is it supposed to be with sound? Because we can't hear it.
Yes, you don't hear the sound?
When you press share screen, there's a little square that you can press to share with sound.
Share screen. Advanced.
Stop sharing. Stop sharing, and then when you press share screen again, there's a place to click on. Before you choose which screen to share, there's a place to click on that says share with sound.
Okay. Share sound. Sorry.
Okay.
Okay, from the beginning. Tell me if everyone is here.
Water, energy,
yes.
Food.
Thank you.
All essential to human life and all interconnected. How so? Let's start with the most basic element, water. We need water to make our crops grow and to produce our energy. For instance, to cool power plants and to grow biofuels. Every year, the world uses 580 billion cubic meters of water for energy. That's over 200 million Olympic-sized swimming pools. But we also need energy to treat our water and to transport our food from field to table. Take this steak. There's more to it than meets the eye. It took over 3,000 litres of water to make this steak. And producing it used 35 times more energy than you'll get out of it. The world is hungry for food. Food is hungry for energy, and energy production is thirsty work. These three essential resources are already under stress, but soon they will be pushed to their limits. By 2050, the world will have 9 billion mouths to feed. Between now and then, we'll have to produce more food than we've produced in the last 8,000 years. More food means more energy, and that means we're going to need a lot more water. But in a changing climate, we're going to have to achieve more with less. Water, energy, food. The connections just keep growing. Understanding their interconnections is the essence of Nexus thinking. Designing smart and sustainable policies is the essence of Nexus action.
Okay. So I'm going to share back my presentation. Okay. Okay. So as the video said, and this is really important thing to understand, that up until now, each subject in each sector was examined separately. So we have energy researchers, and we have water researchers, and we have agriculture researchers. But basically what we are saying is that the nexus requires a holistic thinking, because everything is connected. We are producing energy, and we need this energy to pump water, and we needed to harvest and to use agriculture machinery. We need to grow biomass for fuel. We need to use the energy to desalinate water. And Israel itself is relying on desalination. This is the water that you are drinking in Israel. And also we are now examining the opportunity or the chance to also irrigate with desalinated water, and how it will affect the crops. We need the water to irrigate agriculture. So everything has to do together. So these interconnections, it is something that we must take under consideration when we research and when we determine policy, because it will affect each impact from energy policy will also determine the impact on the agriculture and the water supply. So when we're talking about the sustainable, the UN sustainable goals, we can see that it has a major, the nexus, this interconnections between energy and water and food has a major impact on many of the sustainable goals. Of course, if it's proper nutrition to fight poverty, it will create more job opportunities. It has everything to do with water stress and clean water, of course, and all the impact on the land, the impact on our resources. So again, it's only strengthened how much we need to move forward to some kind of a holistic approach when we look on the way to adapt to climate change and how we look at global projections and deal with them. I have another video here. I hope now I will learn how to do it like properly. We'll stop sharing. Okay. Sorry, I didn't share with sound. So 1 minute. So this is just when we're talking about dual use of land, just a nice video to look at. No sound. Like that. On and on. I watched it like 3 million times because it made me funny.
I need to start my day every day with that video.
No, it's a very good video. I totally agree. This is a very good video, and not just that it's a good video, it really shows that everything is combining together, because we need major land available to deploy renewable energy facilities. So this will definitely will have to do with, there's not really available land. So it has to go all on agriculture, all on other land that used for herds. It will definitely be close to our house. Of course, dual use also mean that we will deploy, if it means PV. In Israel, PV is highly relevant because we are a very sunny country, but we can see that other countries that are not so sunny, like Germany, also deploy a lot of PV installations. So if it means over roof or over water reservoirs, so this is dual use. We're actually using the land to produce electricity, and either if it's to grow food or to feed the livestock, which is also give us, of course, it's part of our nutrition. If it's for living or for growing also fish. In Israel, we're also deploying now, it's kind of new, but it's also done in other parts of the world to cover with PV panels fish pools. So you can still grow fish and to produce electricity. And of course, it has to find, and we will talk about it, some kind of the optimum point where the fish, for example, gets enough light so they can continue to, we are not hurting their quality of living, and we still can, the productivity still remains the same. And of course, we're also producing electricity from renewable energy. Opa, sorry, took me again. Sorry. Okay. So when we're talking about agrivoltaics, which is the main issue of today's lecture, we're talking about deploying PV panels over agriculture fields. As I said, there's a lot of examples for dual use, but this is what we're focusing in because this is actually what the nexus means. We are still producing food, we're maintaining food security while producing renewable energy. So you can see here that up until now, we have land that is used for energy production and land that is used for food production. And if we want to combine the two, we have to deploy the PV panels above the crops. And we have other implications that we're going to talk about it, but I will say briefly that these PV panels, we also assume that not only we can use both for energy production and for food production, we also believe that while we are covering the land and we're creating a shade, then evaporation will decrease and we can also conserve more water for irrigation. So there are not many countries in the world right now. I think only Massachusetts in the United States and perhaps Japan that actually using or implementing agrivoltaics as part of energy policy and also determine the proper regulation. But for now, most of the projects that we will see around the world are pilots, all kinds of demonstration pilots. And it involves a lot of different crops, different sizes, different lands and different soils, of course, and also a lot of interesting technology. So we can see also the different kinds of deployment of each, and we will see more examples of each facility. Because the main idea, as I said, is to find the optimum point, because we know that crops need light to photosynthesis. So we cannot cover them completely. It has to have some, they have to photosynthesize. And we can see at the right pictures, we see vineyards. And we know that grapes especially are almost non-shade tolerant. They do like 8 hours of photosynthesis the day, which means that the moment the sun is rising and almost until the sun is almost the end of the day, they need to do photosynthesis. So they're trying, you can see, I don't know if you see my arrow, this is the one setup, and you can see here another different kind of setup. So the main idea is to try and shade as little as possible and taking under consideration that sun is moving during the day. So in any part, the grapes will probably receive some kind of light. We also know that they can do photosynthesis in periods, like 3 hours now and then 3 hours later, because now it's shady. So it takes a lot of repetitions that we need to do in research to find out the most valuable point to produce electricity and to maintain crops productivity. We see here in Vietnam, I'm sorry, I forgot about Abigail. Can you help me?
Yeah.
Sorry, Chita?
Oh, wheat.
Wheat, thank you. So you can see here wheat, and also we must take under consideration that grapes is great for wine, and of course it's a part of our quality of living. But in some parts of the country, we have to take also under consideration food security and necessities that we must have in our diet, and wheat is one of them. Also, wheat and maize are completely shade intolerant. So trying to raise them under shading conditions can tell us a lot about how we can adapt to climate change and to feed 9 billion people. So this is also another interesting setup, and you can see here it's a very interesting technology in the Netherlands, that the panels are almost transparent. We can see that the light is going through the panels, and we see here some kind of strawberries. Strawberries also, they have very delicate conditions that need to maintain to make sure we are make sure that get the high quality of terms for highly production. So, and also here there's some kind of lettuce in Chile. And this is Japan, and we can see rice fields. And again, this is really interesting because you can see how the shade is spread to make sure that the rice is getting enough light during the day. Okay, this is really advanced. And I think this is right now, this is the most advanced application that I've seen so far when we're talking about vertical systems. But it has to take under consideration, and you can see here that vertical systems, even though they're considered a very interesting opportunity for land use or for agrivoltaic, you can see it creates a lot of shade during the day. So that means, and we will talk about it more, that we need to make sure there's enough distance between the rows, so plants and crops will get enough light during the day, because it's really shady. And this is just the future, what we can see on the left corner, on the left image. So when we're talking about parameters to take under consideration when we're thinking about policy, because when we determine policy, we need to establish what parameters planners and farmers should take under consideration. So of course, we need to think about the system size, because the larger it gets, of course, we produce more electricity. However, the larger it gets, that means that more what kind of crops can deal with this amount of shade. Because when systems are small, the plants really get a lot of light because the sun is constantly moving. But the larger the facility is, that means that all that is really centered in the center of the system is almost completely shaded. And I will show you more examples. Of course, we have to take under consideration PV configuration. if it's fixed panels, or we're doing tracking systems, or we're doing vertical systems. Every system has its pros and cons. Of course, again, some of them will, the electricity will benefit more, and some the agriculture will benefit more. And this is part of finding the optimum point to balance. It of course affects the height, the width, and the turning clearance for farm equipment. Height is determined with what kind of equipment we're working in each farm. Some work with, some are working with the large tractors that are 3 meters high. So that means that our facility has to be higher than the tractor. This also affects how we can maintain this facility, because the higher it is, it will be difficult to clean and difficult to take care of. So it makes it more expensive. That means that when the higher it is and expensive it is, that will most definitely affect the size, because we're not doing small system size, which are quite high, because then farmers will lose money. Also taking under consideration, as I said, the shading and how we can maintain weed and pest control. It is argued that because of the shade and because the evaporation is lower, and while we're preserving water, the land stays moist for longer, and the moisture it gets, it is a very preferred ground for pests to grow. So that means maybe that we will have to do more pest control. Maybe we'll have to use stronger chemicals. We are not yet sure. I don't think there's enough of research for that. And this is why we have to have some kind of evaluation parameters. When we're determining policy, and of course, policy will start with pilots. And there are some things that we have to make sure that regulation keeps track on, which is the productivity of the crops or herd, as we saw, which means that after, when we harvest, we have to wait the harvest, wait the crops. Did we had any kind of impact on the biomass, on the herd size, the success of the growth, the actual productivity, any kind of crop management, as we saw, any kind of treatment if related to the soil, to the irrigation systems, diseases and weed management. And of course, what is the potential changes for the future? We will revise the crops that we are growing. We will want to grow more herds, the grazing needs. And this brings me back to our little country and the research that we are conducting here in the Arava, which is the southern part of Israel. We are doing an agrivoltaic research. It's a small facility. We have, maybe before we start talking about this, maybe we should, if someone has some questions before we're diving in to this research.
Anybody have any questions?
No?
I guess not.
Okay, so I can move on. Okay, so this research is combining several institutions that are were partnered with the Dead Sea and Arava Science Center, also the Arava Institute, with the Arizona University in the United States, and with the Southern Larva R&D, which are, this is the agriculture experimental farm. It is all funded by the Jewish National Fund in the United States. And you can see here that this is this nice facility that we built here in the region. This is how it looks from above, and you can see the planting underneath. It's quite small. It's 100 square meters at the moment, but we are interested in making it bigger. And this is really the first trial that we did. It's important. You can see here that we put these are fixed PV panels. They are positioned in the best angle for the Arava to produce electricity. It's about 30 degrees. And because we were quite late in planting season, what we did at the first trial is really to make sure that all systems are working. We grew lettuce and radish. And what we really wanted to see, and this is what we want to see also further ahead, is what kind of implications we get from this agrivoltaic facility. So we're thinking that we will see a reduction in water demand for irrigation. We hope to see increased biomass production because we are thinking that it might be that some of the crops will actually enjoy the shade. We see that the sun and the radiation is becoming harder each year. This is thanks to climate change impact, of course. So we were thinking that perhaps some of the crops will actually benefit from shading and from the decreased temperatures thanks to the irrigation and the slower evaporation. And it will create some kind of a chiller, cooler microclimate beneath the panels. Because of this cooler microclimate, we assume that it will increase the solar panels efficiency. We see that the higher the temperature outside, the efficiency of the PV panels decreased and they produce less electricity. So we want to see if indeed the cooler climate beneath the panels will decrease their temperature and then they will produce more electricity. And of course, as I said before, to see if shade intolerant crops can grow in the shade. Especially important crops for food security and for valuable nutrition like maize and corn, and also some kinds of vegetables like tomatoes and cucumbers and potatoes. This is a really highly important for nutrition, highly relevant, especially for underdeveloped countries, which are suffer more from climate change impact and from food security, insecurity. So this is the first round of crops. As I said, we grew lettuce and radish. This is the biomass that we produced. And we can see here, this is the radish. So plenty of radish and plenty of lettuce, and the initial results, which are yes, they're quite initial because in order to say that this result actually affected by the shade or not affected by the shade, we have to have some kind of we have to grow again lettuce and radish. We have to have some kind of repetition in the research. One cycle is not enough. But for initial results, we didn't find any differences between shade and sun radish. But we did see that the shade lettuce had a better start than the sun lettuce. However, the growing rate was slower. So that made us thinking that also shade can have other effects. and it's especially important for farmers because that means that we're prolonging the season, we are prolonging the growth. This means that one, perhaps we can produce some kind of agriculture crops that we're prolonging the season. This means that if we weren't supposed to have fresh lettuce in August, we can enter the market with fresh lettuce. And we can also, for farmers, that means that they can charge a higher rate on lettuce, on fresh lettuce, and this will increase their the revenues. Also, this is interesting to think that we might grow some specific crops that are not grown during the summer, but thanks to the shade, we can grow them during the summer. So it has a major impact on food security, the fact that we can maybe change or play with the seasons that we're growing certain crops. So as I said, this round of planting was quite short. It started late and we had to harvest before crops reached maturity, but it enabled us to establish some kind of measurement protocol, to install equipment, and to have preliminary insights. And this is also quite important for pilot research. And when we determine policy, it is also important because at the beginning, we had some, we weren't so sure if we want to plant, even though this is late in the season. But, and that means that we will be delayed in starting our research in like almost 4 or 5 months. And this is a long time. So even if researchers are done with building the facility in a specific time of the year, which is not the proper time for planting, policymakers need to urge them to start the research, even though this is not the proper time of the season, because it gives the opportunity to do a lot of other measurements that are very important. Okay, so we harvest in June, and we waited for almost 2 months to plant again because of the summer in the Arava. We have a very difficult summer. Temperature is rising, and it's almost impossible to work outside. So many farmers actually harvest at the beginning of the summer, and then there's some kind of sanitation period, which is the land is actually resting, and we don't have to use any kind of pest control because we're not growing anything. So there's no room for pests to rely on. And then we're going back to plant at the beginning of September, mostly when the temperatures are decreasing. So this year we made some changes. First, we plant different kinds of crops, and also we made some changes in the structure. And you can see here that we actually lowered the panels of the right pergola, and we added some wooden plates to create more shade. We said that this is important for us to try and figure out the differences between 50% shade, which means 50% cover of the PV panels, and more dense kind of deployment, because this really allows us to produce more electricity. And you can see here, so we have 3 layouts. We have 100% shade and 50% shade. And when I'm talking 100%, 50%, this means 100 PV shade, PV cover. And we also have, of course, a control plot, which is in full sun. And Also, we made some changes that before we plant only lettuce in one pergola and only radish in the second pergola. And we decided to do a variety of crops and to grow them simultaneously to make better use of the land and the time, and to simulate actually living conditions of a community that is doing more of a permaculture instead of mass production of agriculture and of crops. I didn't mention this before, and I think it's a good time to say that we are dealing this research. It's the first of its kind facility in Israel. So it's highly relevant for Israel, which is quite short in land and needs to establish multiple sources to increase the renewable generation of electricity. And of course, it has major implications of climate change with the increased temperature and very high radiation, and we're stressed with water. But this research specifically, when we're looking ahead to implement this kind of model in underdeveloped countries. And I will talk more about it. But because this is what we're talking about, more of a community needs, and to implement this kind of thing in a community and not as a major, for major production, not for electricity or for agriculture, but for community needs, then, and we're talking about food security and diverse diet, then we have to grow multiple kinds of crops at the same time. So this is our crop plan. We started with planting at the end of August, and we planted tomato and butternut squash and green onions, and we are planned to plant corn and teff, which is kind of Ethiopian flour, of Ethiopian wheat, and celery. And you can see here in the picture the differences after 2 weeks in between the plots. So you can see the differences between the full sun and the 50% PV shade and 100% PV shade. And you can see that the leaves in the 100% PV shade are larger. And this is because they are stressed with light. So they're trying to increase their leaves to reach the light. This is a very important insight, because this means that when we're growing leafy kind of plants like basil or spices that will mainly rely on the leaves and not on fruits, then maybe they can actually benefit from shading, because they're increasing the leaves, the size of the leaves. We are also tracking the soil moisture, and you can see here, this is tensiometers, and we are actually monitoring how wet the soil is. And this is all technology that we can follow 24 hours via our phones. It has smart applications. We're also measuring soil temperature, because we're interested to see if the temperature of the soil is decreasing thanks to the shade. Of course, with the differences in meteorological parameters between the full sun and the shade, and the differences in time of vegetation, of flowering and fruiting. This is after 1 month, and I want you to look at the differences between, I didn't write here, but I will explain. I see now that this is missing in the presentation. As I said, we're growing green onions are here. The setup is the same in each plot. Green onions and butternut squash and tomatoes. This is full sun. This is 100% PV shade, and this is 50% shade. And you can see the major differences in the tomatoes and the growing phase, the growth rate, major differences. Also, it's hard to see here, but you can see the different sides. The leaves are actually bigger in the 100% shade than in the full sun. Someone has questions before we're talking about it, before we're moving on?
Yes, hi.
Yes.
Reminding everybody when you ask your question, then also present where you're from.
Good morning. I'm from Armenia, and I have two questions. I'm not an ecologist. I'm a mechanic in my job. But first of all, I would like to thank you for your presentation. It is highly informative and very interesting. And I have two questions. They're as follows. First of all, are there any researches or studies on how this photovoltaic panel impacts the fruit? So you are talking about the shades and the leaves, but for example, in Armenia, we grow grapes, and if it receives a little sun, the grapes, the fruit themselves will not be ripe. And in our life and in our nature, we have very little natural things left. So we would like the natural things to stay with us. So physically, these grapes and tomatoes, the fruit themselves, do they stay the same in terms of taste and quality? Because as a rule, when there is little sun, the quality and the taste is lost. So are there any studies and researches on this impact of shade and the little sun? And my second question is whether you have any studies on PV panels, on water PV panels. Do you have any research on water PV panels that are installed on lakes? So how do they impact nature, environment, and the living beings under the water? Thank you.
Thank you for the very important questions. These are very good questions. So they did some research about grapes, mainly in France, and we also grow tomatoes, but you can see that we haven't cropped them yet. We haven't harvested them yet, but yes, we should do tests for sugar and some kind of test exams, and to see how it impacts the taste and the size and the and the nutrition that we get out of it. I know that first of all, I would be happy to send maybe through Abigail some kind of literature for you to read. And so in your own time, you can read some literature, because this is really interesting. I can tell you that in some of the research that we are doing in the experimental farm, we do some taste tests to see how it impacts the taste of the watermelons, for example. So I don't know specifically on grapes, but yes, research should deal with the impact of how the shade, not only on the leaves, but also how it impacts our quality of living. This is highly important. We don't want to eat fruits that has no taste. So I can tell you that we are going to do this in our research. We are starting harvesting tomatoes right now, and I will be happy to share the results with you once I have it. Yes, when we are determining policy, I also think that is highly important, and I will also say it in the end, not only to do only biomass, but yes, to see how it impacts the quality of the fruits or the vegetables. And regarding the second questions, I know in Israel, it's still in pilot stages. When we are talking about PV panels that are deployed over water reservoirs and fish tanks. So yes, you have to find, you cannot cover them all. It has to be in a small portion of the lake because we still have living ecosystems underneath, you know, inside the water. And of course, if it uses for aquaculture. And there's also a very big work that's been done, I think last year, about deploying PV panels over water reservoirs. And I will be happy to share it with you and to send it through Abigail. And you can read there some of the initial conclusions. I hope I answered. Okay.
Yes, thank you very much. Thank you.
Okay, any more questions?
Yes, Natasha.
She's muted, so maybe she can't hear her.
Oh. Natasha? There you are.
Hello to everyone. I'm Natasha from Energy Agency of the Republic of Macedonia. I would like to mention that in Register of the Renewable Energy Sources in the agency is published a photovoltaic power plant of 50 kilowatt in the municipality of Studenicani, where the photovoltaics were placed in the height of 3 to 5 meters, and under them, their vegetable plantation. However, this is a house whose owner is not actively engaged in agriculture. But the problem with this power plant is that if one of the panel amount break down, the replacement will be more difficult. And I will ask to, how do you deal with it? Thank you.
Yes, so I agree. This is part of the issues that needs to take under consideration, because we need to take under consideration that mechanical equipment should cross the fields, and to maintain so the structure won't get hurt, it has to be quite high. And yes, I think that if when we need to do some kind of economic evaluation and to see if the maintenance is quite expensive, then perhaps it's affecting the economic viability of the structure, because if at the end it will cost more money for maintenance, and the electricity generation and the food production won't cover the maintenance, then perhaps it is not suitable for this type of field. For example, I know that in Israel, one of the pilots, they wanted to deploy PV panels over avocado plantation. And avocado tree can reach about 5 meters, even 6 meters high. So that means that the structure will be at least 7 or 8. This is you need I don't know if there's a proper equipment even to maintain this kind of high facility. So of course it is I think that before doing any kind of pilot, it has to come with some kind of economic plan, definitely, and to see if it's even possible to maintain, because we also need to think ahead. And if we're doing this kind of facility, it's for 20, 30 years. Any more questions? I see someone is talking, but okay, that's right. No more questions? Okay, so I will move on. Our model, we had a lot of considerations how we want to for the electricity production of this facility. And since we are focused on underdeveloped countries, and the main problem is the lack of infrastructure, both water infrastructure and electricity infrastructure. And this is relevant for underdeveloped countries, but I think it's also relevant for developed countries, also in Europe and also in Israel. Infrastructure, to deploy infrastructure is highly expensive. It needs to be maintained all the time. Population is growing, so this means that what is deployed in the past not necessarily will provide the needs in the future. So that means we have to deploy new infrastructure, more electricity lines, more water lines. And not only that it's highly expensive, it also it takes a long time. To deploy infrastructure can take about an average like 10 years. And 10 years, as we discussed earlier, it's quite a lot. So going off grid or going mini grids or macro grids, this is I think anyway, this is the future. Because the more that we're trying to provide for smaller areas and to provide the entire needs of a small area or even a medium-sized area, the better that we can do maintenance. We can cut transmission losses. It would be easier for the grid to absorb renewable energy that is not always stable, and it will be less affected by it. So this is part of the reason why we wanted to go off grid, because I think it will be a great research and a great example for how future structures of renewable energy facilities should look like in the future. And so for us, and you can see here, off-grid agrivoltaics actually provide the needs again for water, energy, and food. It improved it gives crop protection and could increase crop yield. It provides electricity to communities. Also, we can deploy AC, which is now we can see that already now in Europe, people are dying of heat. The heat waves are so extreme, and Europe is not at all air conditioned. And we can see that the next 20 years, when we're talking about the energy demand, will all go for air conditioning. It will be slowly, but obviously every house in Europe will eventually have air conditioning. We cannot live without it, especially that it's getting hotter and hotter. So it's a large consumer of energy. I can tell you that in Israeli summer, most of the energy consumed in the residential sector is for cooling. And it's going to be like this all around the world, obviously. So going off grid or going in a mini grids, it will enable communities also to deploy air conditioning. And for food processing and for any kind of mechanical vehicles, we see that also the agriculture is going forward to electricity mechanics. Everything will be electrical, also tractors and any kind of heavy machinery. Everything is going to be charged and use unattached to wires. So it's also something that needs to be, when we're thinking of the future, we need to take it under consideration. Also, we're going forward to be very, very precise in the agriculture needs. And as I showed you in my research, we are already using, and we will use more kinds of sensors, and it will be very accurate kind of agriculture. And it's highly important because of climate change impact, and because we are short in resources, and we have to be very, very smart on how we are using these resources, both for land and for grow crops and for using water, and of course, for using energy. So that means we have to be to deploy as many sensors and many parameters and measurement variables to measure different kinds of variables in a smart way. But also, I'm saying also it hasn't had to be quite expensive. So, but it will run on electricity and it will run on some kind of Wi-Fi. So the best that we can do is to provide, again, as I said, a holistic model that provides the water and the energy and the food in the same place. So for us, in the future goals of this year research period, we're also going to deploy some kind of water technology. Here in the region, what is relevant is desalination. Is a desalination facility, because the water here are very salty, and the saltier it gets, the soil is affected. After years of irrigating with salty water, some of the land is so unnourished, so we cannot plant in certain plots anymore. So part of the research is also to see if we can irrigate in desalinated water. However, what kind of supplements we need to add to the water to maintain proper nutrition that the crops needs, and also for human being needs, because we're drinking desalinated water and it has to have certain vitamins and certain added nutrients to the water that in regular pumped water we usually do have in irregular tap water. So this is relevant for Israel, but for other parts of the world, maybe some kind of purification technology is needed, because water is so contained, so it has to be some kind of purifying mechanism or purifying technology. And of course, it consumes energy. It consumes a lot of energy. So using the energy that the PV panels are for purifying water or desalinate water, to use it for irrigation. So we can use smart irrigation that of course is working on electricity. Most of the world today actually flood the fields, and the fields are flooded with water. It also consumes a lot of water, and it's not quite healthy for the crops. So when we're talking about being very accurate, This also means that we can use the electricity that now many communities around the globe do not have in their fields, so they can actually irrigate in a smart way, and this will allow and enable to implement smart irrigation solutions. I have some policy recommendations, and I know that most of you are policy people. And all this presentation really discussed of the future needs that we need to take under consideration that are relevant for everyone, of course, not only for underdeveloped countries, but when I'm talking about policy recommendation, this is a recommendation that also fits Israel. And first and foremost, we have to estimate the potential of agrivoltaics in the country. And as Natasha mentioned, they approved an agrivoltaic facility was built in their country, but it is quite high. And now they're having major issues on how to maintain the PV panels. So as I said, the avocado example that I gave, even though we really want to dual use of land, it might not be relevant in certain parts of the country. So first and foremost, we have to estimate what's the potential, where it is exactly, and then what kind of deployment needs, what kind of the deployment needs that we want to establish. And that means for the planning aspects and also for the environmental impact. For example, in Israel, we have a lot of very large PV facilities, grounded PV facilities, and for the safety of the population, we use fences all around. Fences actually impact the living ecosystem. It prevents from animals to move around. It changes really everything of. Sometimes they use a lot. It creates a lot of noise, for example, or they use a major light. So during the night, they can monitor what's going on in the field. And we also know that strong lightning affects living ecosystems. So we need to take under consideration in every renewable energy project the entire aspects, both of the planning and both of the environmental impact. And it's not mentioned here in the slide, but also the economic impact and the economic implications and how much it's going to cost, because pilots are encouraged by the country. But at the end, we want communities and we want to go off grid or mini grids. So communities and regions and cities are going to deploy these kinds of facilities. So we don't want to make a negative impact in the end of this kind of projects. As I mentioned in the off-grid project, pilots should include R&D, which means that if we can deploy in a pilot project of agrivoltaics, and we can deploy and implement new technologies, new and advanced technologies, startup technologies of any kind of tracking systems, PV panels tracking systems, any kind of algorithms that can control the tracking systems. It was mentioned before the impact of the shade on the grapes. So if we can create, and there are some kind of startups today in the world to create some kind of algorithm that can control the tracking system and control the shading periods during the day, this is highly important for later implementation and later deployment of agrivoltaics. Any kind of accurate agriculture, irrigation or machinery, or trying new kinds of crops that you don't grow in your country at all or in the region at all. And this means that we can play with also with the kind of crops, with maybe new kinds of crops that are genetically engineered to consume less water. So I believe that every pilot project, because we are looking, and this is really takes us to the energy, water, and food nexus. It has to include all variables together. I can tell you that today, if you want to implement any kind of renewable energy facility in Israel, they're only looking on the energy. How much installed capacity, how you're going to connect it to the grid, if it has, yes, what kind of environmental impact. Not sometimes they're not, they yes or not take it under consideration, but we need to look, this is exactly it. We need to see all the time, how can we implement research that includes the water and the food and the energy all together. And once we take this under consideration, when we as policymakers initiate a new kind of tender for pilots, I encourage you to take all these variables under consideration, and to pick the ones that actually supports the entire this entire system and the entire interconnections between energy and food and water together. Which brings us to the electricity tariff that we are that is determined for pilot phase. Usually, the new and more advanced and more startup-y the technology is, it requires more funding. So this means that we have to provide a better electricity tariff for startups. And usually countries are not, they prefer to support the known and the larger facilities that you can give a low tariff, and then we actually neglect both the R&D side of pilot projects, and we don't really support the different areas and different crops and different technologies that we can implement. So in order for us to enable an optimal research practices and for precise agriculture, we need to take under consideration that perhaps it is better to provide a higher tariff and maybe support less projects, but we will have diverse conclusions and diverse insight that further on we can implement in a larger scale. This is it, and I would be happy to answer more questions if you have. Or if you want to share from your experience regarding difficulties in policy implementation, or where you have encountered in any kind of this conjunction between the needs of different resources of water and energy and food.
Do any of you know of experiments like this that you do in your countries? I mean, I assume if it happens, you would know. Tali, could you please stop sharing your screen?
Oh, sorry. I got stop share. Okay, sorry.
Do you have any dual land usage experiments in your countries? Yeah, Gordana.
Good afternoon to all of you, and thank you for your presentation. We are just estimating our potential for agrivoltaics in our new strategy for energy, and we estimated that we have potential in agriculture area with wheat, with grains and crops. Did you do any research on wheat? Do you have any experience? How does it impact on wheat?
Thank you, Gordana, for the question. Actually, I'm planning to plant wheat, an Ethiopian kind of wheat, next season, which is in about a month. And I don't know currently. I don't have any research that I know of a conclusion from research on wheat, but I do believe it's very important, just because we said that grains are the foundation of nutrition. So, and they're highly, intolerant shade kinds of crops. So I do think it's very important to conduct research on grains. And of course, even though it will be at least 6 months from now, that we will have some kind of initial results on wheat, but of course, I would be happy to share whatever we will find out at the end of this year.
Thank you.
And I can also look for some research that dealt with wheat and to share it with you.
Thank you.
Abigail.
Please, Tali, if there's any additional reading material, please pass it to me, and everyone, I'll add it to our Google Drive. There's
Yes,
already the article that Tarek was talking about. It's already up there, for example, from Thursday.
I would be happy to.
Thank you. Does anybody else have any questions or examples from your own countries?
I will also say that we are very much enthusiastic in collaboration. So because there are not a lot of agrivoltaic facilities, if you know in your country researchers that are looking to collaborate, we would be more than happy to engage. So please, we can definitely keep in touch, and yes.
That's good to know. So everybody keep your ears and eyes open for anything like that in your own countries. Georgian team, you always have questions. Where are you today?
The problem is that we don't really have such systems in Georgia, at least for now.
You don't have what? I'm sorry, again?
We are not really developing agrivoltaics at the moment. We don't have large installations.
Okay.
No.
Okay. Anyone else have agrivoltaic installations or plan to in your countries? Or it's a brand new topic for you?
I guess it's new.
Okay.
Okay,
New is always better.
great.
So, thank you, everyone. If you have any more questions, you have my email, and you can feel free to contact me. I will provide all the literature that I think is relevant, and Abigail will upload it to the Google Drive. And I hope you enjoyed this presentation, and I wish you to the rest of the course to be very interesting and insightful for all of you.
Yeah, Tali, we'll see you in the final session also.
Yes, you will.
Great.
Thank you very much.
Thank you, Tali. Okay, everybody, this today was short and sweet. We will see you all tomorrow, same time, same place. I hope everybody received my email about the projects. Everything that Suleiman discussed in the very first session, we realized that it was a lot of information in a very short time, and it seemed that it was a bit confusing. So we kind of reformatted it. If everybody can come tomorrow prepared with a question or a problem that you are working on in your country that has to do with renewable energy, short presentation about it. We expect everybody to present tomorrow something very short, just to bring up a question. At the end of Suleiman's session, Suleiman tomorrow will be talking about the life cycle analysis of a PV system. He'll be talking about that for about an hour and a half. And then the last hour of the session, because remember tomorrow is 2.5 hours, we will be doing the project with him. And so come with a presentation, and then we'll all be working in a group to think about different possible solutions and ways that we can learn from each other, which you will then present in the very final session, a presentation about your work process and maybe solutions that you have come up with through learning from each other. Okay, so please come with problems from your own countries, prepared to present them tomorrow, very short and sweet. And we'll see you tomorrow morning or afternoon, wherever you are. Have a good day, everybody. Bye.
Thank you. Bye.
Bye.
Bye.